Good day, everyone. And once again, we're back together. All right, so this time we are looking at electric circuits. Right, let's jump into it. All right, so they say to us, we've got the circuit below that is connected to a battery of unknown EMF and internal resistance, right? So there's our battery setup, okay? And they're using a rheostat in that case. They say a student varies the current through the circuit by varying the external resistance, all right, which is R in the circuit when the switch S is closed, right? They say they measure the current in the circuit and record the readings on the voltmeter across the battery. And these readings are recorded in the following, in the table below, right? So now they've given us these values over there. Right, so the first thing that they ask from us is to plot the graph of the reading on the voltmeter versus the current, right, on the x-axis, on the graph paper that is below. Okay, right, so what I've done, ladies and gents, first of all, I've just plotted the points onto the graph. Let me just explain my rationale, right? So already they had given us current, a scale for current, but for voltage, we're not given a scale. In fact, I need to write it down over there. Right, so then what I did was to plot the points that are given there. Now, I chose a scale of 5 because if you look at your voltage range there, it starts from 9 till 18.7, right? So the highest value would be 18.7, right? But I still need a value for voltage when the current is 0, and you'll understand that later, right? So I started my reading from 0, right, all the way till 20. And when I look at this, because of I have got divisions there, so I divided them in terms of 5 so that I could accommodate 18.7. Okay, right now, so which means each increment, and I want you to please notice this. So each increment in this case will be in terms of 0.5, right? So what do I mean? I mean this is 0.5, that's 1, that's 2, 1.5, that's 2, that's 2.5, and so on and so forth, right? And how you do that is that you will always take the difference between two segments, right? In this case, and you divide, or rather you subtract from each other and you divide by the number of lines in between, and you'll see that we've got 10 lines, right, per division. So as a result, that would be 0.5. Okay, right, so now I'm ready to draw my graph. Okay, so I've plotted all my points that were given in the table, right? You'll see the first one, for instance, was 0.8 and 18.7. Okay, just to show you there, right? So here I've got 18.7, right? All right, let me just try to get that point there. All right, so in this case, what do I have? I've got 18.7, so I wanted to use a ruler actually, so that I could show you. So 0.8. Now you can see the current values increase in ones, right? So my values for current, can you see? If you go there, sorry, not 1 rather, it will increase in terms of 0.1. So that's 1 minus 0 divided by 10. So they increase in terms of 0.1. So where would be 0.8 in this case? Now let's take our ruler, right? So that would be 0.5, 6, 7, and 8. So there's 0.8. And we know that our voltage value was 18.7, right? Now if you look at this, we've got 17.5 over here, right? So that would be 18, right? That's 18.5. This is 19 over there, but it should be slightly below 19 because we're looking at 18.7. Okay, so it is that point over there. Right, so I did the same with all of the other points, and now what I'm going to do is just try to draw a line that connects all of my points, right? So it looks like this would be my line over there, right? So I'm going to just connect those dots. Okay, so there it is over there, right? Okay, so there is my graph. Okay, so we can go on to the next question. Right, now they say to us, calculate the gradient of the graph, right? Show the values that you used in your graph and include the appropriate unit in your answer. So what I did, or rather what I'm going to do is I'm going to take the first and the last point that I was given, right? So I'm going to take that point over there, right? 18.7 and 0.8. And I'm going to take those points there and I'm going to calculate my gradient from there, okay? Right, so in this case, if I'm to calculate the gradient, the value of M, okay, that's going to be change in Y, which is our voltage, divided by change in X, which is current. Okay, sorry, that should be big V, right? So that's change in voltage divided by change in current, right? So I'm going to take my values. Okay, so that's V2, which is 18.7, minus V1, which is 9.0, okay, divided by, when the voltage was 18.7, the current is 0.8, okay, and my current value is 6.3 when the voltage was 9. Okay, so there it is there. Right, please remember to maintain that order there. Okay, so we've got 18.7. Okay, maybe let me do this. So this would be 18.7 minus 9, okay, divided by 0.8 minus 6.3. Right, so I get a value of negative 1.76. Okay, so that would be my value for the gradient. Now, they said to you, show the values that you used, okay, and your on your graph rather, and include the appropriate unit in your answer. Okay, right, so in this case, let me do this. They said show the values that you've used on your graph. So let me call this V2. Okay, so this would be 0.8 as well as 18.7. And the other value was this one where we've got, okay, 6.3. Okay, so 6.3 and the voltage was 9. Okay, right, there we go. Those are the two values that we used. Now they said also include the unit in your answer. Right, so if you think about it in this case, so the unit that we have would be voltage divided by current, so that's volt per ampere. But I want you to think about it, ladies and gents. Right, so if you're working with voltage and current, V is equal to I times R. But when I've got V over I, what does that give me? You're absolutely correct, right? That would be resistance, isn't it? So that means this is voltage per ampere, which in this case would be ohms. Okay, right, so there it is over there. Okay, so they say use an appropriate equation and your answer to question 8.1.2 to calculate the internal resistance of the given cell. Now guys, I want you to please keep this in mind. So we've got voltage against current, right? So which means if I were to, if you think about it, we are relating EMF. So we know we usually have EMF is equal to V external, okay, plus current times the resistance. Now, if you think about it, so this is V external plus V loss, or you can say V internal, the voltage across the internal resistance, right? So now we want to make V external the subject of the formula, right? But remember, V loss is the current times R, right, times the internal resistance, right? So how do I make sure that I make V external the subject of the formula? So if I take everything to the left-hand side, I will have, okay, let me actually do this. V external is equal to I times R, right, plus, or rather minus EMF. In fact, it should be EMF minus I times R. So that's EMF minus I times R. Now remember, current is your X value, right? So we can put it this way. It's minus R times I, or I times R, right? Plus EMF. So this makes sense why our graph has got a negative gradient, right? Now I want you to note, guys, this becomes our, so if you think of the normal straight line equation, y is equals to mx plus c, right? You've got the coefficient there, you've got the x variable. So our x variable is current, so which means the coefficient is minus r, right? Which is the gradient, okay? And of course, this forms our y-intercept. So therefore, it means that the gradient underneath this graph actually gives us the internal resistance. So therefore, the R value should be equal to 1.76 ohms, the value that we calculated over there, right? So our internal resistance should be 1.76 ohms, right? Now, they say to us, without a calculation, determine the EMF used in the investigation, right? Briefly explain how you obtained this value. So if we go back to that y is equal to mx, okay, plus c, right? So you'll see, what is the EMF? It's going to be our c value, which is the the y-intercept, okay? In fact, so that should be our y-intercept. So in this case, what does that tell us? It tells us that the EMF value, we will get it from our y-intercept, right? This is where the current is equal to 0. So let's go to the graph. Okay, where is the current equal to 0? It's exactly at that spot over there, right? At that spot over there. I would say 20.1 or even 20, right? So our EMF value would be equal to 20 volts. Okay, if you want to, you can say 20.1 if you want to, right? So our EMF is 20 volts. Right, let's go on to the next question. Right, so they say to us, what will be the value of R when the current flowing in the circuit is 4 amperes? All right, so now we know that we've got the EMF value. You remember we've got that 20 volts there, right? We know the current value, and now we also know the value of the internal resistance, right? So we can say, well, that's going to be EMF. We know that EMF is equal to I. All right, so that's plus the small r. I'm not sure why I changed my the color of my pen. Right, so that's 4 amperes over there. We know that our EMF is 20. We know that our internal resistance, or our external resistance rather, which is what we want, and our internal resistance was 1.76. Okay, right, so I'm going to divide both sides by 4 in this case. Okay, and what would be my R value? Right, so that's 20 divided by 4, that gives me 5. And what is 5 minus 1.76? Okay, so that's 3.24. So which means our resistance value will be 3.24 ohms. Okay. Right, and of course, our accuracy level might be different, of course, depending on, the values that you interpreted or you derived from the graph. Okay, right, now let's go on to the next question. Right, so they give us a circuit there, which has a bulb that are connected to a 12-volt battery with a negligible internal resistance. They say the emitter reads 6 amperes and the power rating of the bulb is 60 watts, right? Firstly, they want us to calculate the resistance of the bulb, right? So now we know in this case, if we've got total current, in this case, there's the total current moving outside of the battery. But once we get to that node, what happens to the current? It will divide. Some of the current will go through resistor R and some of the current would go through that bulb. So what can I say about those two, the resistor R and the bulb? They must be in parallel with each other, right? So they will divide current in that case, right? So if they're in parallel, what else do we know? You know that the voltage is the same across them. So if you notice, we're given the voltage in this case as 12 volts. So that means the voltage across R will be 12. The voltage across the bulb will also be 12. So we can say, right, we know the power rating of the bulb. So power is equal to V squared over R, right? So our power rating is 60. Our voltage is 12 volts. And we want the value of R. And in this case, that's going to be R. So that's 60R is equal to 12 squared, which is 144. And we can divide both sides by 60. Okay, so let's get that value there. That's 144 divided by 60. Okay, divided by 60. And that gives us 2.4 ohms. All right, so our value for the resistance of the bulb, rather, let me say our bulb, okay, right, is equal to 2.4 ohms, right? Now they say to state Ohm's law, right? Remember, Ohm's law simply says the current across a conductor, right? A conductor is directly proportional to the potential difference provided that temperature remains constant. Okay, right. So you don't write it this way. Of course, you're going to write it in full, right? So the next question, they say, calculate the resistance of the resistor R, right? Now, I want you to note, ladies and gents, resistor R in this case is in parallel with our bulb, right? We've got the total current, right? And we also have the total resistance in this case, right? The total voltage, right? In this case, the external voltage. So we can get R external, right? Or alternatively, right? We can do this in different ways. We already know the resistance of the bulb, right? We can find out how much current is passing through that bulb. In fact, let's do that. I think it's much more easier, right? So what would be, let's call it current I2. That's in fact, let's say current through the bulb, man. Okay, we know the voltage there. And we know the resistance of the bulb. So this is going to be 12 divided by 2.4. So what should be the value of the current that's passing there, right? So that's 12 divided by 2.4. Okay, so that's 5 amperes that's passing through the bulb, right? Now remember, our total current was 6 amperes. They told us that we've got a total current of 6 amperes. So which means the current that is passing through the resistor R will be 6 minus 5, which gives us 1 ampere. Now that we know the current that's passing through resistor R, we also know the voltage of it, so we can find out what that resistor is. So we know that therefore R is equals to V over I, right? So it's a 12 volt. It's 12 volts over that resistor, and the current is 1. So we get a total resistance of 12 ohms, right? Okay, please keep that in mind. So as I said, what we could have done is we could have found out what is the R external value. So R external would have been, now I'm just exploring an alternative method, right? Would have been V external divided by I total, right? So remember, V external is 12. What is our total current? That would have been 6 amperes that was given, right? So which means that R external would actually be 2 ohms. But you know that 1 over RP, R parallel, right, is 1 over resistor R plus 1 over the resistance of the bulb. Okay, so you've got RP, in this case, the parallel resistance. Okay, you can get that by finding V over R, right? So that was 2 ohms, and we know that R in this case is what we want, and the one of the bulb is 2.4. So you can find it using that formula there. All right, ladies and gents, let's go on to the very last question. Right, so they say how much energy will be used in the resistor R, right, by the resistor R in 2 minutes. Now remember, when we want to find out the energy across a bulb, all right, a resistor, right, what do we have in that resistor? Now we know the current that's passing through that resistor. We said it's 1 ampere, all right, and we know the resistance of the bulb. So I could use either I squared R multiplied by time, okay, or I can use V squared over R times T, or I can say V times I times T. Either one will definitely do in that case. So I'm going to say the current passing there is 1 ampere, the resistance is 12, and the time, they said in 2 minutes, but remember time must always be in seconds, so that's going to be 2 times 60. Right, so let's find that out. That's going to be 2 times 60 multiplied by 12. Okay, 1 squared is 1, so that will give us 1,440. And remember, energy is measured in joules. Right, I hope that makes sense, ladies and gents. And in essence, that is how the cookie crumbles when it comes to that question. I hope that that has been helpful. Otherwise, please look out. Okay, I'm still going to go through, in this case, electrodynamics, right? Of course, including the Faraday's law. All right, so I'll see you guys in a few. Sharp, sharp.